March 4, 1944, Rechlin Air Test Center, northern Germany. A captured Lockheed P-38 Lightning stood on the concrete apron near Hangar 7. The twin-boom fighter's polished aluminum reflected the pale winter sun. Its dual Allison VR-1710 engines were cold, the propellers locked in feathered position. Around it, a team of Luftwaffe engineers prepared their instruments for examination. Among them were specialists from Messerschmitt, Focke-Wulf, and Junkers. Each carried a clipboard, ruler, and notebook issued by the Rechlin Ministerium. The aircraft had been captured after a forced landing near Avignon, France. It was transported in sections by rail to Germany in January. Technicians reassembled the airframe with precision, matching serial numbers on each panel. The U.S. Army Air Force's markings were still visible beneath hastily applied German stencils. Oil stains from previous operations covered the nacelles and undercarriage struts. The nose-mounted armament, one 20mm cannon and 4.50 caliber guns, remained intact. The lead engineer, Hauptmann Karl Behrens, ordered a systematic inspection. He began with the wing spars, noting the unusual configuration of the central pod. Measurements confirmed a span of 52 feet and total length of 37 feet. The elevator linkage extended through the twin booms, an unconventional design for European standards. Behrens wrote, "Asymmetric drag appears compensated by high-power loading." Another technician, Lieutenant Friedrich Adler, examined the turbo-supercharger housing. He identified the General Electric BR-13 units positioned aft of each engine. Copper piping led through the booms to intercoolers beneath the tailplane. Such arrangement, he noted, allowed the Lightning to retain power at 8,000 meters. At the far end of the hangar, a Dornier engineer sketched the electrical system layout. He remarked that both engines could operate independently or in unison. Switching circuits permitted flight on one engine without losing hydraulic control. Fuel tanks in both wings and central pod provided a combined capacity exceeding 400 gallons. When fitted with external drop tanks, the aircraft's range surpassed 2,000 kilometers. A clerk from the Luftwaffe Technical Bureau compared those figures to the Bf-109G. The difference in endurance was more than double. Outside, a camera crew from the Luftnachrichten Regiment documented the inspection. Each component was photographed for technical analysis. Film reels would later be reviewed by the technical office in Berlin-Adlershof. Nearby, a Messerschmitt pilot observed quietly, his cap pulled low against the wind. He commented that the Lightning's heavy structure must reduce maneuverability. Behrens responded that its twin power plants likely compensated at higher altitudes. The test crew drained the remaining American fuel from the tanks. They refilled it with standard German C3 aviation fuel. Engine startup was scheduled for the following morning, weather permitting. Barometric readings showed moderate pressure with low humidity, ideal conditions for testing. Each propeller blade was inspected for pitch alignment and surface erosion. The flight control cables were retensioned to manufacturer specifications. As daylight faded, the metallic outline of the aircraft stood against a gray horizon. Its twin tails, angular and symmetrical, contrasted with the single-finned German fighters nearby. The engineers concluded their first day with a detailed inventory report. Under the general remarks, Behrens wrote, "Construction quality superior. Fit and finish consistent with mass production." No further comment was added regarding flight performance. That would come only after the first test sortie scheduled for March 5. By nightfall, guards from the Airfield Security Detachment took position around the hangar. A tarpaulin was drawn over the cockpit canopy. The aircraft remained silent under the dim light of sodium lamps. For the Luftwaffe engineers, the next day would reveal how an American twin-engine fighter had forced Germany's best pilots to reconsider everything they knew about power and altitude. By early 1944, Luftwaffe command faced an irreversible shift in air superiority. Allied escort fighters now accompanied heavy bombers deep into the Reich. The P-38 Lightning, once considered an odd American experiment, had become a key instrument of that change. Its combination of twin engines, turbo-superchargers, and range allowed operations over targets previously unreachable. The aircraft had first appeared in Europe in late 1942 with the first fighter group. Initially, German pilots underestimated it due to its large size and twin-boom design. Reports from JG-26 and JG-2 described it as ungainly and unsuited for dogfighting. However, by 1943, those assumptions were contradicted by combat records. P-38 squadrons demonstrated reliable climb rates above 7,000 meters. Their turbo-supercharged Allisons retained power where single-engine fighters lost efficiency. German analysts began collecting field reports on the Lightning's engagement over Italy and France. At Oberpfaffenhofen, engineers at Messerschmitt's research office examined intercepted photographs. They noted the unusual cooling system and intercooler duct placement. Unlike the Bf-110 or Me-10, the Lightning's layout allowed both engines to remain within the central aerodynamic envelope. This reduced asymmetric drag in single-engine conditions. American field manuals later confirmed the aircraft could maintain altitude on one engine at 20,000 feet. Operational units such as the 14th Fighter Group used the Lightning for long-range escort over North Africa. From Tunisian bases, it reached Sicily and southern Italy with drop tanks. Luftwaffe reconnaissance aircraft photographed contrails from twin-engine fighters above bomber formations. Initial intelligence summaries misidentified them as twin-seat variants of the P-47 Thunderbolt. Only after direct encounters did German pilots recognize the twin-boom configuration. The Technical Office of the Reich Air Ministry opened a study under file number GLC 1943-78. It classified the P-38 as Type Zweisitziger Fernjäger, long-range twin-engine fighter, single-seat. Measurements taken from recovered wrecks were incomplete. Most examples burned upon impact, leaving few components intact. Thus, the Lightning at Rechlin represented the first undamaged specimen available for comprehensive evaluation. At the time, German twin-engine fighter design faced its own limitations. The Me-10 and Bf-110 carried heavy armament but lacked altitude performance. Their engines, primarily Daimler-Benz DB603 and DB605, struggled above 7,500 meters. Turbo-supercharging remained a persistent weakness in German engineering. Due to shortage of suitable high-temperature alloys and precision machining tools. Attempts to replicate the American turbocharger principle, using exhaust-driven turbines, had failed by 1943. Most Luftwaffe designs instead relied on mechanical superchargers with limited pressure ratios. By contrast, the P-38's twin General Electric turbo-superchargers gave consistent power output beyond 25,000 feet. Captured manuals from North Africa describe the system's automatic wastegate control, allowing smooth throttle transitions without manual boost correction. To the Luftwaffe engineers, this automation represented both technical and industrial superiority. It required precision control valves and temperature-resistant bearings unavailable in Germany's wartime supply chain. Strategically, the Lightning also filled a niche the Luftwaffe had never achieved. It combined long-range escort, reconnaissance, and interception roles in one airframe. While Germany built specialized aircraft for each task, the US standardized production to a few adaptable types. Lockheed's assembly lines in Burbank, California, produced over 10 P-38s daily by 1944. Each left the factory with standardized components compatible across production batches. By the time the captured Lightning reached Rechlin, its operational reputation was established. It had flown photo reconnaissance missions over Berlin, escorted bombers over Munich, and intercepted German transports across the Mediterranean. Allied air intelligence considered it an essential transition between tactical and strategic air power. In Berlin, reports from Rechlin drew the attention of General Galland's technical advisors. They wanted performance data compared directly with the FW-190A and the upcoming Me-262. For the engineers at the airfield, this was not an academic comparison. It was a test of whether German engineering could still compete in precision, altitude capability, and range. The evaluation scheduled for March 5 would include full power runs, climb tests, and range estimates. The Luftwaffe technicians prepared pressure gauges calibrated in inches of mercury. Fuel consumption would be recorded per engine, with altitude increments every 1,000 meters. Photographic plates and oscillographs were set up to capture manifold pressure readings. It was a methodical process, scientific, repeatable, and essential. By dawn, the engineers knew they were not testing a mere curiosity. They were examining a design that had already changed the balance of the air war. March 5, 1944. Rechlin Air Test Center. 7:40 hours. The P-38 Lightning stood positioned at the northern runway, engines preheated by portable generators. Air temperature was 2 degrees Celsius, wind calm from the west. Ground crew secured the aircraft chocks while engineers adjusted turbocharger control valves. The objective: measure climb performance and engine efficiency at high altitude. Test pilot Oberleutnant Erich Müller, formerly of Erprobungskommando 25, received briefing orders. He was instructed to maintain a constant power setting of 1,500 horsepower per engine during ascent. A chase aircraft, a Bf-109G equipped with barometric sensors, would record comparative data. The first engine start occurred at 7:52. The Wright Allison VIR 1710-89 came alive with minimal vibration. Oil pressure stabilizing at 90 psi within 12 seconds. The left engine followed, showing identical readings. Observers noted smooth synchronization without torque yaw, unusual for a twin configuration. Müller taxied the aircraft to runway position, rechecked propeller governors, and released brakes at 7:59. Takeoff roll measured 340 meters before rotation. Initial climb rate registered 4,200 feet per minute. By 3,000 meters, manifold pressure remained constant at 44 inches of mercury. With exhaust gas temperature stable below 700 degrees Celsius, a value few German engines could maintain. The Bf-109G following at maximum power began to lag by the 4th minute of ascent. At 6,000 meters, observers on the ground recorded contrails from the P-38's twin booms. The turbo-superchargers emitted a steady, muted whine audible even from the airstrip perimeter. Data loggers confirmed both engines retained nearly full rated output. The test pilot radioed, "Boost holding. Temperature within limits. Handling stable." By 8,500 meters, airspeed held at 420 kilometers per hour in climb configuration. The Lightning reached 9,000 meters in 9 minutes and 38 seconds. This exceeded the estimated ceiling of the Bf-109G by more than 1,200 meters. At altitude, Müller tested single-engine performance. He feathered the left propeller and maintained flight level for 62 seconds, without measurable altitude loss. Turbo output from the active engine remained at 42 inches manifold pressure. Control stability was rated satisfactory in his post-flight log. Engineers on the ground exchanged brief comments but withheld conclusions until post-sortie analysis. Upon descent, the aircraft maintained consistent cooling under reduced throttle. Cylinder head temperatures equalized at 180 degrees Celsius upon landing. Fuel consumption data showed 240 liters used for the complete test cycle. A result confirming high efficiency relative to German twin-engine fighters. In Hangar 7, the engineering team dismantled the turbocharger ducts for inspection. The bronze bearings and turbine housing revealed minimal wear. Behrens noted that the American use of nickel-chromium alloys allowed continuous operation above 750 degrees Celsius without structural deformation. This metallurgical stability explained why the Lightning could sustain long climbs at high boost. Adler compared the P-38's turbo assembly to a captured P-47 component previously examined at Augsburg. He observed similar design principles but a more compact configuration in the Lightning. The unit's weight, 38 kilograms per turbo, was half the mass of German experimental equivalents. The automatic wastegate actuator, connected by pressure lines to the cockpit, operated flawlessly. A small aneroid capsule maintained pressure balance during throttle variation. Behrens wrote, "Operation appears pilot-independent, self-regulating, highly reliable." Electrical analysis revealed redundant generator systems powering all major instruments. If one engine failed, flight controls, radio, and armament remained functional. German aircraft of similar class lacked full redundancy. This redundancy explained the Lightning's record of returning from combat with one engine disabled. The engineers also measured wing loading at 43 pounds per square foot, comparable to the Me-10 but with superior climb rate and ceiling. They identified the combination of laminar flow airfoil and turbo-supercharged thrust as the defining factors in its altitude performance. The propellers, Curtiss electric constant speed models, adjusted pitch automatically, based on engine RPM and manifold pressure, ensuring constant efficiency. Following the inspection, data sheets were dispatched to Berlin Adlershof for evaluation. A summary line read, "Twin-engine configuration exhibits exceptional climb, high-altitude capability, and endurance unmatched in German operational types." No mention was made of aesthetic or design impressions. The conclusions were purely mechanical: precision, reliability, altitude retention, and efficiency at power settings unachievable by domestic production. By evening, the Rechlin team completed its first full assessment of the P-38 Lightning. It was no longer viewed as an unconventional curiosity. The engineers had witnessed quantitative proof that two synchronized turbo-supercharged engines, if managed correctly, could outperform any single-engine fighter Germany had built. The laughter that had greeted its shape now gave way to calculation. A silent acknowledgment that American engineering had mastered what German factories could no longer replicate. March 6, 1944. Rechlin Air Test Center. Morning frost covered the concrete as the P-38 Lightning was rolled out again. The engineers planned controlled level speed trials at 7,000 and 9,000 meters. The test objectives were to verify power retention and determine specific fuel consumption. Oberleutnant Müller took off at 8:11 hours. Climb to test altitude was achieved in 9 minutes and 16 seconds, slightly faster than previous runs. At 7,000 meters, the aircraft stabilized at 565 km per hour true airspeed. Manifold pressure remained constant at 42 inches, turbo RPM steady at 22,000. Observers from the ground confirmed smooth exhaust pattern, minimal oscillation, and stable contrail formation. The engine performance graphs later revealed less than 3% power loss per 1,000 meters of altitude gained. At 9,000 meters, Müller recorded a cruise speed of 580 km per hour. He transmitted, "Control response firm. Boost automatic. Temperature normal. This steady behavior contradicted German expectations for a twin-engine aircraft of that mass. The test data showed the Lightning's aerodynamic efficiency exceeded calculated projections by 12%. A comparison table drawn that afternoon displayed clear ratios. At similar weight, the Me-10 required 200 more horsepower to achieve comparable altitude. At operational range, the P-38's fuel endurance nearly doubled. In the hangar, Behrens reviewed the oscillograph records. Each trace line represented manifold pressure and exhaust gas temperature across time. He marked both curves as consistent, an annotation rarely used in German test summaries. The absence of surging or power drop-off indicated complete turbo balance under continuous load. Adler concluded that American engine control systems had surpassed German practice in automation. He pointed out that the pilot workload was significantly reduced compared to mechanical boost management in the Bf-109 and Fw-190. During a meeting that evening, technicians from Junkers and Daimler-Benz joined the discussion. The subject was production feasibility. Could such turbo-superchargers be manufactured under German conditions? The consensus was negative. High-temperature alloys for turbine blades were unavailable in sufficient quantity. Even experimental units at Dessau had failed after short endurance tests due to material fatigue. Behrens summarized, the design is replicable. The metallurgy is not. Attention turned to the aircraft's dual-engine safety advantage. Operational records from Allied intelligence confirmed numerous cases of Lightning pilots returning on one functioning engine after sustaining battle damage. In Luftwaffe service, similar incidents with twin-engine fighters often ended in forced landings. The difference lay not in piloting skill but in system design. The P-38's complete electrical and hydraulic redundancy allowed continued control. Power steering remained functional through dual hydraulic pumps, one per engine. The German equivalents lacked such integration, relying on shared systems that failed if one motor was lost. By midday, the engineers compiled a performance comparison chart. Altitude ceiling, P-38, 12,200 meters, Bf-109G, 10,800, Me-410, 10,100. Maximum climb, P-38, 4,200 feet per minute, Bf-109G, 3,700, Me-410, 2,900. Operational range, P-38, 2,200 kilometers with drop tanks, Bf-109G, 850, Me-410, 1,050. Fuel efficiency ratio favored the American aircraft by nearly 40%. The figures were confirmed by multiple cross-checks. There was no error margin significant enough to alter the conclusion. Behrens drafted a formal report to the Technisches Amt in Berlin. He wrote, subject, Lockheed P-38 Lightning, evaluation of operational efficiency. Paragraph 3 contained a simple statement. The Lightning demonstrates an altitude performance beyond current domestic capability. The twin-engine configuration does not hinder, but enhances, climb and range. Turbo-supercharging ensures constant power at operational altitudes of 8,000 to 10,000 meters. No German airframe in production matches its sustained output. When the report reached Berlin, senior engineers within the Luftwaffe Technical Division reviewed the findings. Some dismissed them as irrelevant due to resource shortages and industrial constraints. Others saw them as a warning. If Allied fighters could operate at that altitude with such endurance, then the Reich's air defense network faced a systemic disadvantage. The Lightning's capability to escort bombers from bases in Britain to the heart of Germany nullified the earlier reliance on interceptors limited by short range. Late that night, Behrens met privately with Adler to summarize their conclusions. The conversation was brief and factual. Behrens stated, "We have reached the technical ceiling of our single-engine development." Adler replied, "Then this," he gestured toward the aircraft, "is the next generation." No further comment was recorded in the daily log. The test phase was officially marked as complete. For the first time, the German engineers recognized that twin-engine efficiency and high-altitude endurance, once dismissed as impractical, had now become the foundation of Allied air superiority. March 7, 1944. The P-38 Lightning remained parked in front of Hangar 7 under partial disassembly. The engineers had removed engine cowlings, intercooler ducts, and turbo units for metallurgical sampling. The objective of this final inspection phase was not performance testing but production analysis. Berlin had requested an evaluation of whether German factories could reproduce the key systems. Material samples were labeled for transport to the Reich Metallurgical Institute in Spandau. Each bearing, pipe, and bracket was weighed and catalogued. The turbocharger's turbine blades, cast in nickel-chromium alloy, drew particular attention. Behrens noted their consistent grain pattern and lack of visible fatigue after multiple high-temperature cycles. In contrast, German exhaust-driven turbines, such as those used in the Ju-288 project, showed pitting and oxidation after fewer than 10 hours of operation. This single difference explained years of German difficulty with turbo-supercharged aircraft. The Rechlin metallurgist, Oberingenieur Kruger, summarized his findings in one sentence. "Industrial quality control in American aviation appears superior by magnitude, not by chance." He cited uniformity of casting, precision in machining tolerances, and the anodized protection on fittings. The German war economy, strained by shortages and bombing, could no longer sustain that level of production consistency. Intelligence officers attached to the technical command correlated these findings with aerial reconnaissance of U.S. factories. Lockheed's Burbank facility operated under strict process standardization. Machine tools were electrically synchronized, and turbine components were mass-produced with identical specifications. This automation contrasted with Germany's semi-handcrafted engine production methods. In practical terms, it meant that every Lightning that left the assembly line performed identically. German fighters, even within the same model series, often varied in engine output by several percent. In parallel, analysts in Berlin examined captured mission logs from Allied units in Italy and France. Reports confirmed the Lightning's operational reach. Flights from Corsica to Munich or from Sardinia to southern France were routine by late 1943. The aircraft could escort bombers beyond the Rhine, return safely, and still conduct reconnaissance photography. This endurance rendered German defensive sectors ineffective at depth. Fighter commands could no longer predict where and when escorts would disengage. Production statistics reinforced the disparity. By January 1944, the United States had produced more than 6,000 P-38s. Germany's combined output of Mi-10 and Bf-110 fighters during the same period totaled fewer than 1,500. The Lightning's dual-role versatility reduced the need for specialized variants. American logistics distributed one adaptable platform across multiple theaters, whereas Germany maintained separate aircraft for reconnaissance, escort, and bomber interception. This efficiency magnified the strategic advantage of American industrial scale. The Reichsluftfahrtministerium's subsequent memorandum referenced the Rechlin report directly. It described the Lightning as the optimal form of the two-engine single-seat fighter concept. It noted that despite structural complexity, the aircraft's operational benefits outweighed maintenance costs. Its dual-engine reliability, high-altitude endurance, and long-range performance met all criteria for sustained offensive and defensive missions. The memo recommended renewed research into advanced turbocharger systems, but acknowledged the shortage of materials and precision machinery. No project proposal followed. Meanwhile, Luftwaffe field units continued to encounter P-38s over the Mediterranean. Radio intercepts from 3 JG-53 described the aircraft as untouchable above 8,000 meters. Pilots reported that attacks from below were ineffective due to the Lightning's rapid climb response. When engaged, its heavy armament concentrated in the nose provided stable firing accuracy. The centralized gun installation eliminated convergence problems common in wing-mounted weapon designs. At Rechlin, Behrens compiled the final data charts. The concluding sheet contained a section labeled Strategische Bewertung, Strategic Evaluation. It stated, the P-38 Lightning represents the practical solution to high-altitude, long-range, single-seat fighter design. Its turbo-supercharging enables consistent power above 8,000 meters. Its redundancy and range exceed any current Luftwaffe type. Future aircraft must incorporate similar dual-engine configuration if industrially feasible. By that stage, the recommendation was academic. Germany's remaining resources were diverted to emergency interceptor programs such as the Me-262 and Ta-152. Neither could replace the Lightning's endurance or multi-role capability. The Rechlin engineers concluded their report with a formal closing line typical of wartime documentation. Further evaluation suspended, subject type no longer available in operational condition. The aircraft itself was moved to storage within Hangar 12. Its engines drained, its propellers removed for technical preservation. The data had been gathered, the results confirmed, and the implications clear. For the Luftwaffe, the P-38 Lightning demonstrated not only aerodynamic and mechanical superiority, but also the industrial reality that determined the outcome of the air war. April 1945. The war in Europe neared its conclusion. Rechlin Air Test Center lay in partial ruins from repeated Allied air raids. Scattered across the field were the remnants of one secret test aircraft. Among them, the disassembled frame of the P-38 Lightning remained stored under a collapsed hangar roof. Its aluminum skin was scorched and bent, but its structure remained largely intact. It had outlasted the Air Force that once studied it. When Allied inspection teams arrived in May, they found crates labeled U.S. twin-engine study. Inside were surviving turbocharger parts, metallurgical samples, and incomplete performance charts. Each document carried the stamp Geheim Kommandosake, strictly secret. The records were transferred to American custody and later archived at Wright Field, Ohio. Post-war analysis confirmed that German engineers had accurately measured the Lightning's performance. Their data matched Lockheed's own production records within 2% tolerance. Former Rechlin engineers were later interviewed by Allied technical intelligence officers. Behrens, taken into custody near Hamburg, gave detailed recollections of the 1944 tests. He stated, "We laughed at the design. It appeared unconventional and excessive. After the first climb trial, no one laughed again. It was beyond our reach." His reports were translated and filed under the U.S. Air Technical Intelligence Division's Foreign Evaluation Series. In 1946, captured German documentation contributed to Allied assessments of comparative aircraft technology. Analysts noted that the P-38's twin-turbocharged configuration represented the most advanced operational use of exhaust-driven supercharging in any wartime fighter. No Luftwaffe aircraft achieved equivalent altitude efficiency during the conflict. The Lightning's development validated a design principle, redundancy and endurance over simplicity. American engineers, reviewing both their own wartime records and captured German materials, acknowledged that the Luftwaffe's technical analysis had been precise and professional. They recognized the German reports as among the most detailed foreign evaluations of an American aircraft. The Rechlin tests became a case study in Allied post-war technical training. students at Wright Field examined photographs of the test aircraft and annotated German schematics. The accompanying caption read, "Captured enemy report confirming full operational integrity of P-38 design." By the late 1940s, the Lightning's design principles influenced several new jet projects. Lockheed's subsequent P-80 Shooting Star retained aerodynamic characteristics derived from P-38 research. German engineers later employed under Allied contracts, including some from Rechlin, participated in early American and British jet programs. Their wartime evaluations indirectly advanced post-war Western aviation standards. Archival summaries compiled in 1952 by the U.S. Air Force Historical Division reference the Rechlin trials in an appendix titled Foreign Technical Appraisals, 1943 to 1945. It concluded, German field engineers correctly identified the industrial and operational factors that distinguished American aircraft production. They lacked only the capacity to reproduce them. The report cited metallurgy, automation, and materials logistics as decisive contributors. Within Germany, surviving members of the wartime research community acknowledged that the Lightning had represented a turning point in aerial engineering understanding. Adler, interviewed in 1953 by aviation historian Alfred Price, stated, "The P-38 proved that twin engines could climb faster, reach higher, and fly farther than any of us expected. It was the end of our single-engine faith." His remarks echoed the internal realization first documented at Rechlin in March 1944. In modern archives, the surviving fragments of the captured aircraft remain catalogued as P-38F, serial unknown. Sections of its right boom, one propeller hub, and a portion of a turbocharger are preserved in storage. Accompanying them are Behrens's handwritten notes. Meticulous entries describing manifold pressure, fuel flow, and altitude readings line by line. Each figure tells a factual story of recognition born from measurement, not emotion. The final notation in his 1944 logbook reads simply, "American design efficiency achieved through production discipline and material science." No further comment follows. It is a precise conclusion, characteristic of the Rechlin engineer's approach. The data spoke for itself. By the war's end, the P-38 Lightning had flown in every major theater. It served as bomber escort, reconnaissance platform, and interceptor. Its twin engines and turbo-supercharged systems remained reliable through diverse climates. For the German specialists who once dismissed it, the aircraft became an enduring example of how engineering foresight and industrial scale had reshaped air warfare into a contest of endurance rather than invention. The Rechlin trials ended in silence, but their implications persisted. In the measured language of post-war debriefings, one statement summarized the experience. The Lightning was not superior because it was complex. It was superior because every component worked exactly as designed. That sentence, entered into the 1945 Allied report, remains the final record of how German engineers learned respect through data, not defeat.